Howdy, folks. Welcome back to another CS 120 Honors lecture. In this lecture, we'll be talking about generics and traits. Generics are something we've seen in the past. For example, when we discussed options and results or vectors, and we use those angle brackets, that's an example of a generic. So today we'll be formally introducing those alongside traits and how you can use those to define functionality a particular type might have. So generics. Every programming language has tools for effectively handling duplication of concepts. In Rust, one of those tools is generics, which are abstract stand-ins for concrete types like strings or integers. We've already seen many examples of generics. Everything between the angle brackets in these examples are generics, and they indicate that these data types can hold data of some generic type instead of some concrete type like integers or strings. So let's look at some examples that'll hopefully make this more clear. Starting with structs, we can define structs to use a generic type parameter using the angle bracket syntax. We declare the name of the type parameter inside of these angle brackets just after the name of the struct. So in this case, it's T, which is the default name most Rust programmers use because T could be short for type. So in this example, we have a point T struct that holds X and Y coordinate values of any type. And we can see in our main function that we've created two different instances of point with different numeric values for their X's and Y's. It's important to note that because we've only used one generic type to define point T, its definition says that the fields X and Y are both the same type. So if we create an instance of point T that has different types for X and Y, like we do in this example on the left, our code won't compile. So to fix this, we could simply change the definition of point to be a generic over two types, in this case T and U, and have X be of type T and Y be of type U. Moving on to enums, we've definitely seen both of these before. We can define enums to hold generic data types and their variants in a similar fashion to how we did with structs. Both of these definitions should make sense to you. The option T enum is generic over the type T and has two variants, sum, which holds one value of type T, and the none variant, which doesn't hold any data or value. And because the option T is generic, we can use this abstraction no matter what the type of the optional value is. The Rust enum is generic over two types, T and E, and it has two variants as well. The OK, which holds a value of type T, and the air, which holds a value of type E. We can also use generic types in the definitions of struct or enum methods. So returning to our point example, we've now implemented a method called X, which returns a reference to the data in the field X. In our method, you can see that we declare T after the implement keyword. By doing so, Rust can identify that the type in the angle brackets in point is a generic type rather than a concrete type. We can also specify constraints on generic types when defining methods. So for example, we could implement a method only on point F32 instances rather than on point instances with any generic type. So in other words, this code means the type point32 will have a distance from origin method. In other instances of point T where T is not in F32, they will not have this method. And finally, moving on to functions, just like how functions take parameters with unknown values to run the same code and multiple concrete values, functions can also take parameters of some generic type instead of some concrete type. So in this example, these functions, largest I32 and largest char, are trying to find the largest value in a list, that being either an integer or a character. However, their function bodies are the exact same code. So let's eliminate the duplication by introducing a generic type parameter in a single largest function. So now we've combined the two largest functions into one, using the generic data type and its signature. And now we need to update our main function to use largest instead of the two separate functions. And now while this seems like it should work, this code will actually not compile. If we try to compile this right now, we'll get this error. The help text mentions restricting the type parameter t using this partial order thing. This partial order thing is known as a trait. A trait defines functionality a particular type has and can share with other types. So we can use traits to define shared behavior. A type's behavior is defined by the methods we call on that type. So different types would share the same behavior if we call the same methods on all of those types. So trait definitions are a way to group together these potentially shared method signatures. For generic types, we can use trait bounds to specify that a generic type can be any type that has a certain behavior. So these bounds restrict the amount of types that the generic type could be. Traits are very similar to interfaces, which is found in other programming languages like Java, for example. So here's an example pulled directly from the Rust documentation. In this example, we have two structs that hold different kinds of text data, a news article and a tweet struct. Let's say we wanted to display summaries of the data that might be stored in a news article or tweet instance. To do this, we might create summarize methods for both of these structs. However, since this method is shared across the two different structs, we could create a trait, which we do on the left here. We can see we've declared a trait using the trait keyword, followed by the trait's name, which in this case is summary. And then inside of the curly brackets, we declare a method signature that describes the behavior of the two types that will implement this trait. So in this case, the method is a summarize method. After this method signature, you can see that instead of providing a implementation of the method within curly brackets, we instead just use a semicolon. Each of the types that implement this trait must provide its own custom behavior for the body of the summarize method. The compiler will enforce that any type that has the summary trait will have a method called summarize defined with this signature exactly. So now that we've defined the signature of the summary trait summarize method, we can implement it on our types. So implementing a trait on a type is very similar to implementing a regular method. The difference is that after the implement keyword, we put the trait name followed by the for keyword, and then we specify the name of the type we want to implement the trait for. And then within the implement block, we implement the method or methods that the trait has defined. So now that the summary trait is implemented on news article and tweet, users can call this trait method on instances of either in the same way that we call regular methods. So in this example, we create an instance of tweet, and then we summarize it using the summarize method, and it will print the following. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accept generic types. So we'll use the summary trait that we implemented previously to place trait bounds on this generic type parameter. So this means that the item parameter now accepts any type that implements the summary trait. So in the body of notify, we can call any methods on item that come from the summary trait, such as summarize. So we can call and notify and pass in any instance of news article or tweet. Code that calls the function with any other type, such as a integer or a string, won't compile because those types don't implement summary. We can also specify more than one trait bound. So say we want to notify to display formatting as well as summarize on the item parameter. We could specify in this definition that item must implement both summary and display. However, using too many trait bounds has its obvious downsides. Let's say we had a function like this that has a couple of generics, both of which have different trait bounds. As you can see, this function signature looks very cluttered. So instead, fortunately, Rust has an alternative syntax for specifying trait bounds using this where keyword. So after the function signature, inside of a where clause, we can define the trait bounds for each of the generic types, which I think this makes things much more readable. So now that we know more about traits, let's return to our largest function and fix it. We know that this error states that the body of the largest function won't work for all possible types of t. We need to restrict the type parameter t to only take types that implement the partial order trait, meaning we can only use types whose values can be ordered. So to restrict the type, we can change the definition of the largest function to only accept parameters or arguments that implement the partial order trait. And now when we run this code, it should compile and print the following. Okay, great. That's all for today. Just some quick reminders. Homework 7 and MP1 are due next Monday. Homework 8 was released yesterday and is due on Wednesday, next Wednesday. Homework or MP2 was also released yesterday and is due on Wednesday, October 11th. Okay, great. That's everything. I'll see you guys next week.